All right, so thank you for that introduction, Alicia. So as you're all aware by now, my name is Jonathan, and I'll be talking about magnetars and how we study the strongest magnets in the universe. Before I get to the topic of magnetars in particular, I want to give a more general look at how we do science in astrophysics. In particular, I want everyone to think about how we study objects in space and how we think about those objects in space. So to answer this first question, we first need to ask ourselves, how do we as humans see? And so if you're not familiar with biology, the way that our eyes work is that we have three different types of cones that allow us to see color. And we also have rods that let us see the intensity of light. For the purposes of this talk, you don't need to worry about rods. You can just pretend they don't exist. But we have three cones that specialize at looking at specific wavelengths of light, in particular red, green, and blue. And you can see here that each of these colors will correspond to a particular wavelength. And there's a lot more information in color than you might expect. For example, if you had no color vision, you might look at this gray blob that was made by my friend Alex at some blackmailing. And you might not be entirely sure what it is without color. But now suppose you turn your color vision back on and you see that it's mostly red. And this might tell you, okay, this is an apple, it's ripe, I can eat it, it will hopefully taste good. On the other hand, if this apple is mostly green, you would think, this is probably a Granny Smith, it could be quite sour, maybe it's better to use in baking. On the other hand, if this apple is mostly blue, you'll think, this is probably not something I want to eat, it might have been painted, it might have been mutated, I should stay far away from this apple, it might kill me. And so there's a lot of ways, and so this kind of highlights how important color is for how we bring context to everything that we see. And in the same way that we get information from color, astronomers can use the full spectrum of light to gain information about all the objects out in space. So if you have not seen this before, this is basically the entire spectrum of light. And you can look at this either from wavelengths, where these are your long wavelengths, to your short wavelengths, or you can look at this from a perspective of energy, where this is lower energy light or higher energy. And so you have a full spectrum here. There's radio, which is about building sized. You have microwave and infrared, which are much, much smaller. You have the visible spectrum of light, which is what we see in. You have ultraviolet, which is responsible for giving us skin cancer. You have X-rays, which if you've broken bones, you may be familiar with. And we have gamma rays, which are the highest energy type of light that we classify. And so what you can see here is that even though we only see this very limited spectrum, there's a lot of information on either side that we can take advantage of to get more information about the things out in space. And so this again brings me to a more general question about how these signals are made and seen. And this is kind of a mirrored question. So if you have a charged particle, an accelerating charged particle will generically create a wave as it moves. And this wave is actually what you see as light. So as an example here, I have a cartoon of what is a charged particle moving up and down. This is actually how your radio antennas will work. The charged particles move up and down, and this creates a wave that oscillates outward that will eventually be picked up by other radio antennas, or for the purposes of astronomers, different types of telescopes. So this is actually a picture of a radio observatory called CHIME. It is the Canadian Hydrogen Intensity Mapping Experiment, and you can see it out in Penticton, BC. So this is one of the biggest radio telescopes in the world. And so when we look at these signals, we can now ask ourselves, well, what kind of things are there out in space that we can see? And for the purposes of this talk, I'll mostly be focusing on stellar objects. So there's a whole bunch of stellar objects. This can be quite complicated, and it's not really the main purpose of this talk. So I'll simplify this a bit. You have stars, and depending on how heavy they are, they'll have three different endpoints. The lightest stars, which include our own sun, will eventually cool into a white dwarf. So this is basically just a remnant that will slowly cool over time. If your stars are heavier, they will eventually collapse and actually explode in what you may know as a supernova. And then depending on the mass afterwards, they'll either collapse into a black hole, which everyone should know as the heaviest objects in space, whereas even light cannot escape their gravity. But if they're not quite that heavy, they will collapse into neutron stars. And these are the things that I study. And in particular, I study magnetars, which are a subtype of neutron star. And so you can ask, before I talk specifically about magnetars and neutron stars, I first want to frame how to think about these objects, and in general, how we think about objects in space. And so I have this somewhat long quote from Enrico Fermi. He was a scientist on the Manhattan Project and had a lot of amazing contributions to physics. And so the quote reads, "I can calculate anything in physics within a factor 2 on a few sheets. To get the numerical factor in front of the formula right may well take a physicist a year to calculate, but I am not interested in that." And so what this means is that you could ask a physicist, how fast is an object going to move? How large is this going to be? And the physicist will say, okay, I know all the physical factors that go into this. There could be 10 different terms. I'm going to do 200 lines of math, and I'm going to give you an exact answer. And a physicist could do that, but you wouldn't see them for like 6 months. And so if you want to build up a quick intuition for something, you can make simplifying approximations. And for Fermi, he was able to calculate these answers within a factor of 2 accuracy. I'm not as smart as Fermi, and so I think about things in powers of 10 instead of powers of 2. And so for a lot of the numbers that I'm going to present forward, or from here on forward, I'm going to use this notation, which is basically powers or scientific notation. If you have not seen this before, if you have 10 to the x, this is just 1 with x zeros. So for example, 10 to the 3 has 1 followed by 3 zeros, which you would know as 1,000. If it's 10 to the minus x, this gets a lot harder to explain in words, where you have x zeros, a 1, and a decimal. Really, all this means is that there's 1, 2, 3 zeros, a decimal. So this is 1 1,000 if it's 10 to the minus 3. We're all good? Okay. And so now we can talk about what neutron stars are. So neutron stars, as I said before, are one of the endpoints of a star. They weigh about 1 solar mass, so as much as the sun, but they actually are only 10 kilometers in radius. And so what's happened here is that they're so heavy and there's nothing to buffer against that gravitational pressure that they collapse. And all of the atoms in the star condense into what are mostly neutrons. And so this 10 kilometer radius is actually about the size of downtown Toronto. So if a neutron star is right on top of us, it would only reach like Don Mills. It's not particularly far away. And so one of the things about this is that a neutron star is incredibly dense. If you were to take a tablespoon of neutron star matter and you brought it back to Earth and it somehow did not explode in your face, it would actually weigh about 1 Mount Everest. So a single tablespoon will weigh as much as the largest mountain. In terms of the structure of the neutron star, I really only want you to think about 3 things. There is the interior of the neutron star here. There is a solid crust, much like how the Earth has a solid crust, which means that you can also get things like starquakes, which are the analogous version of earthquakes here on Earth. The crust of a neutron star will also move around, will shear, and will create starquakes. And finally, outside the neutron star, you have this magnetosphere. You can think of this as like the atmosphere of a neutron star. And this is basically where the magnetic field of a neutron star will dominate. And throughout the talk, I'm also going to use pictures of apples, just to give you a sense of what perspective I'm looking at the neutron star from. So for the example here, this is a slice through the center of the neutron star and its corresponding magnetosphere. So I'll have a lot of apples around so that so it hopefully helps orient everyone at what I'm looking at. And so this is basically a general overview of what neutron stars are. If you want to talk specifically about magnetars, well, as I said before, they're a type of neutron star. They're very bright and they have very strong magnetic fields. And so now you can ask, well, how bright is bright? How do we build an intuition for this? And so we can look at this by relating it in powers of 10 in watts. So watts is a unit of power, so it's energy per second. And to start off, you can relate everything to the light bulb, which produces about 10 watts of power. You can then compare this to a wind turbine, which produces 10 to the 6 watts or 1,000,000 watts of power. So this is 100,000 times more power than the light bulb. Next, you could compare this to the entire energy consumption of Canada, which is 10 to the 11 watts. So this is, again, 100,000 times more power than a single wind turbine. We can play this game again, and we can go even higher up. This symbol represents what would happen if you covered all of the Earth in 100% efficient solar cells. This is the amount of power you'd be able to get. Unfortunately, this image is very wide, but this should be 10 to the 17 watts. So again, 1,000,000 times more power than what Canada consumes. And we can go even higher, and we can look at the power produced by the sun. And this is now 10 to the 26 watts, or 1,000,000,000 times more power than what is produced by covering all of the Earth in solar cells. And so the sun, as you know, is pretty bright, but we can go even further, all the way to magnetars, which are around 10 to the 33 watts. This number can shift around quite a bit. So this is 1 followed by 33 zeros in front of it. And so magnetars are extremely, extremely bright. You might ask, well, if they're so bright, why don't we see them in the sky? You know, I can see the sun. I can't see these magnetars. And the answer is that they're very far away, which is very good for us. If they were as close as the sun was, we would all be dead many times over. And so magnetars are very bright. They have these flares, which are, you can imagine as bursts from the magnetar. And these can be extremely bright, up to 10 billion suns worth of power. And when they're not flaring, they have this quiet mode where even when it's quiet, it's still about 100 times brighter than the sun in X-rays. So again, we should be very glad that they're far away. We would be very tanned. And so the emission of light from these magnetars actually comes from their strong magnetic fields. Their magnetic fields are strong enough that as they slowly decay, the energy in those fields will become light that we see. And so we can ask again, well, how strong are these magnetic fields? How do we build up an intuition for this? If you have forgotten what magnetic fields look like, here is a quick way to visualize them. So I have an image of a bar magnet, and around here are iron filings that will actually follow the field lines. So you'll see here, it goes from north to south, and you can see, you know, these lines. And in these lines, it actually contains energy that the magnetar will convert into light. And so we can look at how to build an intuition for the strength of these fields. And to start off with, I want to look at Earth's magnetic field, which is about 1 Gauss. We can compare this to the next strongest thing, which is actually just a fridge magnet. It's 100 Gauss, so a single fridge magnet is 100 times stronger than the magnetic field of the Earth, which is a little bit embarrassing for the Earth. Next, you have an MRI machine at about 10,000 Gauss, so 100 times stronger than a fridge magnet. Unfortunately, this does not mean that you can just stack 100 fridge magnets and build an MRI at home. It doesn't work like that. Otherwise, you could also use 10,000 Earths, and that would be a little bit more catastrophic. And so, unfortunately, this is where this kind of breaks down. Because if you want to think about the next strongest thing, it's all the way over here at normal neutron stars at about 10 to the 10 Gauss, so 1 followed by 10 zeros. And this is 1,000,000 times stronger than an MRI. But we can go even further than this. And I can go to this weird little symbol here. If you are not familiar with quantum electrodynamics, this is essentially a symbol that I use to represent how charged particles and light interact. And at this magnetic field strength of 10 to the 13 Gauss, your physics starts to change. The way that we imagine how charged particles and light interacting will actually change because of how they interact with the magnetic fields. And your current interactions will change, and you'll actually start to get new interactions that can happen, all because of these magnetic fields. So this is really a threshold where we can start looking for new physics. And past this is where we find magnetars, all the way at 10 to the 15 Gauss. So about 100 times past this point where physics radically changes from what we expect to see on Earth. So really, this is orders and orders of magnitude larger than what we can see on Earth. You know, 10 to the 11, so that's 100 billion times stronger than anything we can make on Earth. I really tried to find images here. It was not possible. Like the Large Hadron Collider is like here. And then it would have overlapped with this image. It would have been really messy. And so just as a recap, a magnetar is a type of neutron star. They're very, very bright, and they have extremely strong magnetic fields. And so at this point, you can ask, well, why can't we just take pictures of these things? I should mention that this is actually just the artist rendition. This is not a picture of a real magnetar, unfortunately. And you might ask why. And so I want to show you this image to talk about what astronomers see when they look out in space. This, if you are not familiar with it, is Sagittarius A star. This is the black hole at the center of our own galaxy, the Milky Way, and is in fact the highest resolution picture taken of an astronomical object, which means it's probably the highest resolution picture ever taken, but the military does weird things, who knows? And so what I want you to focus on here is this size. This is 50 milliarcseconds. If you're not familiar with what an arcsecond is, this is basically a way of measuring how much of the sky an object takes up. And for reference, if you were to ask someone to stand a kilometer away from you and hold up one finger, the width of that finger would be 1 arcsecond. And so this is almost 100,000 times smaller than a person holding a finger from a kilometer away. And to take this picture, it wasn't just one telescope zooming in for, a year. It took a collaboration across many, many telescopes across the Earth, effectively making an Earth-sized telescope. And it took tons and tons and tons of data for months, literal tons of data. They had to fly it in. They couldn't just use Wi-Fi. It would have taken way too long. They had to fly data from the South Pole. It was a lot. And by combining all the data, they were able to make this image. And so this took years and years and years. And so you can ask, well, this is great. How much harder could it be to take a picture of a magnetar? And the answer is that it's still unreasonably hard. Even if you took the closest magnetar to us, it would be 1,000,000 times smaller on the sky. And so that's a lot of improvement we would have to make. For perhaps a better analogy, imagine that you're an amateur astronomer, and you're setting up your telescope for the first time, and you think, I'm going to look at the moon. And if you're good at astronomy, this might be easy. If you're bad at astronomy like me, this might take you a week, because I'm not very good at setting up telescopes. And after a lot of work, you finally get a clear image of the moon. And someone that comes up to you and says, hey, that's a great picture of the moon. Can you show me this ant that I think is on the moon? And you might think this person is crazy. And they would be, because how? Literally how? And so this is kind of how you would imagine if you were to take this picture of a black hole and compare it to a magnetar. That would be what you're trying to do. And so you can ask, well, fine, we can't take an actual image of a magnetar. What do we see when we try and observe them? And the answer is, this is what they look like. So this is an X-ray image of a magnetar around in a supernova remnant. So this is the gas cloud left after a supernova explodes. And in the middle here is your magnetar. So again, I want to draw your attention to this size here. This is now 5 arc minutes, or about 1,000,000 times larger than the image that I showed you before of our black hole. And your magnetar, the image that we associate with magnetar is about 1 arc minute. So about 1,000,000 times larger than the image of the EHT, which was again 1,000,000 times larger than the physical size of your magnetar. So when you look at these things, you're actually seeing something that's 1,000,000,000 times larger than the physical size. And all you're seeing is a dot. So when you look at this, you can ask, well, how do we study these things? What do we really see when we look at this and we take the data? And the answer is something like this. Sorry for blinding everyone whose night vision kicked in. This is a picture of a spectrum. Essentially what this means is you're looking at the intensity of light at every frequency or wavelength or energy of light. So you can imagine this as color information. Basically, this is just telling you how much of each color this is, particularly an X-ray. And this is the kind of stuff that we try and match in theory. Because we can't just see the physical object itself and figure out what's going on, we have to make up models that will explain why we're able to see this particular spectrum, which you can imagine as like a mix of colors. And so for an analogy of this, imagine that I tell you that something you're looking at is 80% orange and 20% green. Well, you can say, okay, that's all the information I have. I'll come up with a couple different theories for what this is. It could be an orange with a leaf. It could be a pumpkin, or it could be a tiger that's about to eat you. And so if you're looking at these images, you might think, well, if it's a tiger, I probably want to know very quickly. And so you can ask yourself, is there more information that I can get? For example, if you see this image in summer, it could be an orange. If you see it in the fall, it's the pumpkin, hopefully. And if it's moving towards you, you probably know it's a tiger and you should run away. And this is kind of the game that we play as theorists, where we try and match these observations. And so, as I mentioned before, we're trying to match basically a whole range of observations. And so we use this information to inform our models. There's color information, as I mentioned before. Sorry again for blinding everyone. There's the spectrum that tells you how much light you have of every frequency. You have brightness information, which as I mentioned before, magnetars can be hundreds to billions of times brighter than the sun. And so whatever theory you come up with has to be able to explain that. And you have timing information. So in the case of magnetars, what we actually learned is that if you look at the total intensity coming from a magnetar as a function of time, it actually repeats itself. And so what this told us is that magnetars spin around. And so what you're really seeing is the same signal that's coming back at you about every second. And so this is what we try and study, and we can ask ourselves, what emits light from a magnetar? And the answer generically is that you have plasma that's creating this light. So plasma is basically hot charged particles. You can imagine, for example, the plasma in the sun. And this is what I try and study. And I try and ask myself, I want to find where the plasma is in the magnetosphere of the magnetar. So in this atmosphere, I want to ask myself, where is this plasma? How is it distributed? And the reason for this is that this tells us, this gives us basically more information or a first look at how these magnetars work. And so you can say, well, this seems simple enough. Why is this so hard to do? And the answer is that magnetars are very weird. As I mentioned before, their magnetic field is strong enough to change physics. You have a lot of different bursts that need to be explained. You have fast radio bursts, you have gamma ray bursts, you have anomalous X-ray pulsars. There's a whole zoo of things that come from magnetars. And so you need a lot of models and mechanisms to explain all the things that can happen. And to fully understand these magnetars, you need to bring together a lot of different fields of physics. Because they're very heavy and very compact, you need to use general relativity. Because they have strong magnetic fields and plasmas, you need to understand electromagnetism. Because these magnetars are made up primarily of neutrons, you need to understand nuclear physics. And as a side note, if you really want to piss off a bunch of scientists, you ask them, you take a room with them and you ask them what colors they think that protons, neutrons, and electrons should be, because no one agrees. I took a poll and it just started fighting. Personally, I think that neutrons should be blue, protons should be red, and electrons should clearly be green. This sounds controversial. And finally, because of how the neutron star crust works, you need to understand tectonics. So as I mentioned before, the crust of the neutron star can shift and create these starquakes, and these will actually create bursts. And so now I can, again, talk a little bit more generally about how we do theory. And there's a little bit of two extremes in these camps. You can do pure analysis, where, again, you take all your math, you do hundreds and hundreds of lines of algebra. Sometimes the problem isn't even mathematically solvable, and it will make you suffer. But has not been my experience at all. And on the other extreme, you can do pure computation. So this is an animation of particles moving around in a magnetic field that was made by one of my friends, Michael, who may or may not be in the audience. And you can see here particles moving around in this magnetic field that slowly coalesce into these blobs. And so you might think, okay, this looks much nicer than this. Why don't we just do this all the time? And the answer is that simulations are really, really hard. And the easiest way to talk about why these simulations are difficult is to talk about senses of scale again. So if you want to imagine the length scales that you have to simulate on your computer, there's a huge range. There's a 10 to the 24, so this is 1 followed by 24 zeros, in range of the sizes of things you need to model. All the way on the smallest end, you have the size of the electron. And then all the way on the extreme end, you have the size of the magnetar at 10 kilometers. and the size of the magnetosphere at about a billion meters or a million kilometers. And so trying to reconcile these two ranges of size requires a lot of resolution, and it's simply not possible for today's computers. But this gets even worse if you look at other dimensions. You can look at time, which is actually about 1,000 times worse. So your electrons will have this time scale at which they wiggle in these magnetic fields, and this wiggling is about 10 to the minus 21 per second. Yeah. On the other extreme, you have rotation of the magnetar, which is about once per second. And on the most extreme scales, you have the characteristic time for your crust to shift and create these starquakes, which is about order of months. So if you imagine trying to take in all this information, it's pretty hard. And it gets even worse, unfortunately. If you try and think about these things in terms of mass, this is 10 to the 60, so 1 followed by 60 zeros of range. And again, on these extreme ends, you have the mass of an electron, which is at 10 to the minus 30 kilograms. You have a kilogram, which you can imagine as a very light dumbbell. And you have a magnetar all the way on the other extreme at 10 to the 30 kilograms. So this is 60 orders of magnitude. And it's simply not possible to simulate currently. And so as an aside, you can ask, well, what was that simulation I just showed you? This was what's known as a local simulation. So the way that scientists get around this currently with their simulations is they either make detailed simulations of very small scale things, or you make assumptions that allow you to make a larger scale simulation. And so this is closer to what I do. When I'm trying to answer this question of finding where the plasma is in the magnetosphere, I use a simplified model to look at how this plasma is made and distributed in this magnetosphere. Again, this is just a slice in the center. And what the simplified model looks like is that you have a very basic emission source, which I highlighted in red here. This is what's emitting light from your magnetar, which is here in blue. And this is a 3D view of an apple, and so a 3D view of your magnetar. And with this basic emission source, you can look at how light is distributed. And then you can use this new physics in a strong magnetic field to see how that light converts into plasma. And so essentially what's happening is that you get two particles of light that will collide and turn into charged particles. And so it's really this interaction that allows us to figure out how our plasma is being made. So as a more technical point, you can ask, well, how do we simplify these things? Again, sorry for blinding everyone. I really did not consider this in the dark room. And so the first two things I do is to avoid real-time calculations. What this really means is that I'm not tracking every single particle of light. I'm not seeing how it collides and turns into plasma for each single particle, but rather I'm averaging over them all to get a characteristic sense of what they're doing. The other thing that I do primarily is to simplify this magnetic field. So here is a more realistic depiction of what the magnetic field would look like in the magnetar, but it's kind of ugly to do mathematically, and I don't like looking at it. So instead, I just do a simple dipole. And so you might ask yourself, okay, you're making all these simplifications. How do you know that what you're doing is even true anymore? And I'd like to argue this kind of through analogy again. Imagine that someone asks you to draw a painting of a dog. And if you're a talented artist, you can whip out your paint, your brushes, and you can get every stroke just right, and you'll get something that looks like this. This is an excellent picture of a dog. I'm assuming everyone who looked at this would say, ah, yes, this is a dog. You might know what breed this is. I forgot what breed this is. However, not everyone is a very good artist. I, for example, am a terrible artist. And so if you ask me to draw a picture of a dog, it might look more like this. And so you can say, well, this wasn't nearly as good as this. There's no detail about the fur, you don't see a tongue, and also it's just, it's a single color. But the point is that if I showed you this, you would still know that this is a dog. And so when we're making these simplifications and we're making these assumptions, the key point is that, yes, we lose detail, but we're still capturing the main characteristics. And so now I can talk more about what I do in particular. And first we can ask, well, what's powering this light around the magnetar? Again, this is a 3D view. And so what's happening here is that when you have these this crustal shearing and this tearing, it will create star quakes, and these star quakes cause plasma to flow from the surface of the star down along the magnetic field line and back into the neutron star. And so these smaller flows are creating light. And we can actually simulate these trajectories that come from this smaller emission structure. And it looks kind of like this. And so what I've shown here, this is the neutron star from a top-down view with your emission structure. And you can see random trajectories that I took from the emission surface, animated. And one of the things I want to point out here, if it's back to a good example, is that your paths of light don't go in a straight line, but they instead curve around the neutron star because of how strong the gravity is. And so, as a reminder, when we're making these models, we want to always try and match observation. And so one of the things that my supervisor did in previous work was to model how the spectrum of light from this emission structure works. And what he found was that if you use this strong physics in the magnetic, or if you use this physics in a strong magnetic field, you can actually get a spectrum. And again, sorry for blinding people. You can get a spectrum that matches this side of your observation. So you get this tail that will actually continue onwards over here. And you can actually recreate this just from using physics and using theory. And so we'll use this light and we can ask ourselves, how is this light distributed? This is again, a slice. So this is the neutron star or magnetar. This is your emission structure drawn out as a cross section. And this is all the light that's being emitted from this structure. And so the key point here is that because of how strong the gravity is at the neutron star, it causes light to bend around. And so almost the entire magnetosphere will be able to see light from the structure. And so, as you might expect, it's brightest very close to the structure. And then as you get farther away, it gets dimmer. And so now that we have a sense of where the light is, we can ask ourselves, how does this turn into plasma? As I mentioned before, the collision of this light is what converts into plasma. And so this is a way to visualize how much plasma is being made. Of course, this plasma also gets lost. It can hit the surface of the star. It can annihilate back into light, or it can even leave the magnetosphere entirely. And so by balancing these factors, you can now get a sense of where this plasma is distributed. And so as you might expect, the plasma is densest closest to the stars, where you get the most plasma. And farther away, you start to get less and less plasma. And so, okay, you might say, oh, well, this is all good. What's the point? And so one of the things that we want to do when we're making these models is to make sure that we're still aligning with observation. And one of the nice things about this is that this actually, we can test that this model is consistent with observation for a couple different ways. One of the ways that we might predict this is, one of the ways that we might think about this is that, well, you have this emission structure, you have this plasma, this is going to hit the surface of the star, and it's going to cause it to heat up. So you can ask yourselves, well, how hot does this magnetar get? And the answer is very, very hot. Close to the emission structure, again, from a top-down view, the magnetar is about 3 million degrees Celsius. So this is not the magnetosphere, to clarify, this is just the surface of the magnetar itself. And it gets to be about 3 million degrees Celsius, down to about 400,000 degrees Celsius farther away. Overall, this is quite a hot object. And it's actually hot enough that if you were to look at how it glows, you would find that it emits light that looks like this. And so And so with our simplified model, what we've actually been able to do is put in this spectrum here from previous work and recover this part of your observation. And so this tells us, okay, our model is actually consistent with what we can do in theory. Or sorry, our model is consistent with what we can do in observation. And so now I can ask, well, now what? And for me personally, I want to check my work against other observations to make sure that they're consistent. There is a wealth of data out there that you can use to check your models and see what things broke. And I also want to check what happens when we make fewer assumptions, get closer to a picture of a real doll. For other people out there, now that we have a sense of these plasma distributions, we can use them to make more precise measurements, more precise simulations of flares. And there are a couple open questions still about these magnetars. Namely, why is the magnetic field so strong? And how do we explain all these different flares and the features we see? So to sum up, astronomers don't just use the visible spectrum, but in fact, the whole spectrum of light to study these objects. And an example of this is the magnetar, which allows us to study new physics because of how strong the magnetic field is. Because this is basically a still recent field, we first want to build up an intuition for what happens by making approximations and simplifying our models. And even though we're making these approximations, we can still get data that is close to observation. And that's all I have to say. Thanks.
Thanks, Jonathan. That was so great. We do have time for questions now. You can probably stay on your slides in case you need to bounce back. Can I turn on a couple lights?
Yeah.
Okay, close your eyes. Okay, yeah.
Stars. That's a star collapsing, yes?
Yes, that's correct.
What happens to all the photons?
So what happens is that, oh, do you want to repeat the question?
Oh, sure. So
Okay.
the question was, what happens to the protons and electrons if the neutron star is made of neutrons?
So what happens is that, so you can compare this to white dwarfs, for example. White dwarfs are held up because the electrons push against gravity, but for neutron stars, it's actually too heavy. And so what happens instead is that your protons and electrons actually combine into neutrons and emit a neutrino, which kind of just flies away. And the reason why they combine is because it's more favorable because of how strong the gravitational pressure is. So you actually end up getting mostly neutrons. There are still some protons and electrons, but yeah, I would say about 90% is neutrons.
Hey, I was just wondering, what percentage of neutron stars are magnetars? And why would a magnetar, what was the process in which a magnetar is produced instead of just a neutron star?
The question was, what percentage of neutron stars are magnetars, and what is the process to produce a magnetar instead of just a regular neutron star?
Yes, so there's on the order of about 1,000 neutron stars that we know of. Of those, I think about 60 are magnetars. So, about 6%. It's still an open question about how the magnetic fields become so strong. You can start to build an intuition for this, where if you look at a magnetic field, for example, of the sun, when it condenses into a neutron star, if you now imagine condensing that into a neutron star, your field lines, because they stay with the surface of the star, must get much denser. And so your magnetic field gets much stronger. In terms of how that then spins up to become strong enough to be a magnetar, it's still really hard to simulate, but there's the most current theories involve using dynamos. So you're basically imagine if you're kneading dough, you're kind of building up strength. It's a similar idea where you're kneading the magnetic fields to get stronger.
Here in the red.
So this is a good question. I wanted to talk about pulsars, which are another type of neutron star. So originally we found pulsars, which are basically rotating neutron stars that emit light from their rotation, or they're powered by the rotation. And so this was a really well-established theory. And then we found weird pulsars, or anomalous X-ray pulsars, that emitted the same amount of light, but were spinning too slowly for that light to come from rotation. And so the observations came first, and then it was theorized actually by my supervisor, Chris Thompson, that instead of rotation, there must be these strong magnetic fields that power this light.
Yeah, Jonathan's supervisor is like the father of magnetars. So you're like the son? The
Sibling?
I don't know. Okay. Yeah.
Some of them, but what usually happens to these magnetars, they are emitting so much energy. So is there another transmission that happens after some point, or they just if they
You'll repeat, or do you want me to?
You can go on.
Okay, yeah. So with these magnetars, the decay of the magnetic field does happen slowly over time. if I remember correctly, depending on, there are other processes that can help maintain the magnetic field. But in the order of like a couple thousand to a couple million years, the magnetic field will decay and they'll no longer emit light. So they'll basically just turn back into regular neutron stars.
Is there anything about your work on magnetars that we have a bearing on this explaining why the sun's atmosphere is so hot? There's a big question.
So the question is, does Jonathan's work on magnetars have any hints as to why the sun's atmosphere, I think specifically you're referring to the corona, is so hot? Yeah, it's a good question.
I would say not directly. That would be more in the realm of computation, or definitely as you make advancements that are, motivated by modeling these magnetars better, you'll also be able to model solar physics a lot better. And so as an example, I know that one of the leading codes for modeling black hole accretion was actually just stolen from old code for modeling solar physics.
Yeah.
Very interesting. Thank you. I just wasn't sure how to think it's interesting that magnetars is related and related. One thing I was wondering about early on, we talked about the orders of magnitude. So we had a picture of the black hole at the center of the Milky Way, and then you said this, but a magnetar would be some amount smaller than that. Can you go back to how those orders of magnitude? That was interesting.
Oh yeah.
How much farther the magnetar is than our Milky Way.
So the question was, Jonathan was showing that cool EHP picture of the black hole at the center of our galaxy, and how many orders of magnitude smaller is the neutron star, right? Well, that was
So basically, this image is 50 micro arc seconds. So 1 arc second is if you took a finger and looked at it from a kilometer away. This is then 100,000 times smaller than that. And then if you were to look at the size of this on the sky, this is 1,000,000 times smaller than that. So 100 billion times smaller than a finger 1 kilometer away.
It's far away from.
Yes, thankfully it's very far away.
Yeah, all the way in the back. You hear that?
What's the crust made of?
What's the crust made of? I have that question too, Jonathan.
So mostly it's still made of neutrons. There are still electrons and protons that are in the crust. And actually the electrons are what allow you to basically anchor the magnetic fields. So the crust, similar to the rest of the neutron star, is mostly neutrons. You still get some protons and electrons there, but yeah.
Yeah.
And most stars use how can
That's a good question. So the question was, if the neutron star is made out of neutrons, which are neutral, they don't have a charge, then what's the theory for how the neutron star is generating a magnetic field?
So there are a couple different theories depending on who you ask. You can talk about how the electrons are spinning and supporting the magnetic field, but neutrons themselves can still still do have a magnetic moment. And so they are still capable of supporting that magnetic field. Even though they have no charge, they still have a magnetic moment.
There's still time for a couple more maybe? Yeah.
So we were talking about how there's a new physics or that you said something like physics breaks down when you're studying things with such high magnetic field as magnetars. So is that physics that we understand, or is that something we just don't understand yet and we're using magnetars trying to develop?
So the question was, Jonathan mentioned that at these really extreme magnetic field strengths that physics breaks down. So do we know what happens there or not, basically?
Yeah, so if you asked, 10, 15 years ago, the answer would be not as well. But actually a lot of the work that my supervisor has done was specifically in the regime of these very strong magnetic fields. And so there's a better understanding of how these particles and light interact now. Yeah, Sorry, I can't remember if there was another part to the question.
Was there more to the question?
Okay, it's more so that, are these magnetars?
Oh, right, yes.
Understand this? Like, what exactly is the new physics?
Yes, so I would say this goes back to we have these theoretical models for how these particles work, and we're able to incorporate magnetic fields in them. And so you can do the math, you can come up with answers that sound convincing and are self-consistent, but you always want to make sure that it's correct. So these magnetars kind of also serve as a check that our math is actually working out and that we're not missing something.
Maybe we can do one last quick question, so you in the back.
Yes. So I know some neutron stars have been observed without binary systems. Has there ever been magnetars? Is it possible to have a binary system or is magnetic field that
There is nothing that would prevent a magnetar from being in a binary with another object. I do not remember off the top of my head, unfortunately, if there is an example of one. But I would not be surprised if there was one. Generically, most stars are actually in binaries. And so if there are about 60 magnetars, I would expect that at least some of them are in binaries, yes.
So I just want to say these are really great questions. So thank you so much for coming and asking great questions. And can we all thank Jonathan one more time for such an